Welcome students. This is another application of Bernoulli's equation, that is orifice meter or orifice plate. It is a device used for measuring the rate of flow of a fluid through a pipe. It is cheaper as compared to a Venturi meter. It also works on the same principle, that is the Bernoulli's principle. Okay, it is a flat circular plate which has a circular sharp edged hole called orifice. Okay, so you have a plate with a circular plate with circular hole. Okay, and it is concentric with the pipe. That means that the pipe, the hole and the plate has the same center. Okay, or same center point. Okay, the orifice diameter is kept generally 0.5 times the diameter of the pipe. Okay, that is the diameter of the hole in the plate is 0.5 times the diameter of the pipe, or half times the diameter of the pipe. Though it may vary from 0.4 to 0.8 times the pipe diameter. It can be somewhere around 0.4 to 0.8. Okay. A differential manometer is connected at section 1, which is at a distance of about 1.5 to 2 times the pipe diameter upstream from the orifice plate, and at section 2, which is at a distance of about half the diameter of the orifice on the downstream side from the orifice plate. Okay, so if you have a plate here, the manometer, differential manometer has two limbs, right? The first limb will be connected and the pipe flow is in this direction. Okay, flow is in this direction. This is our orifice plate. Okay, this is our pipe. Okay, so the first limb or section 1 will be at a distance of 1.5 to 2 times the pipe diameter upstream from the orifice plate. So that is here, section 1. And section 2 will be at a distance of about half the diameter of the orifice on the downstream side. So this is our orifice. There is a hole at the center of the plate. So this is the plate. This is the center of the hole. This is the plate. See, and this is the hole. Okay. So this distance where section 2 is located is half the diameter of the orifice on the downstream side. Okay, that's all. See, okay, so you have here the figure which shows the orifice meter. So the plate is marked here. This is the plate. Okay, it has an orifice at the center, that is the hole at the center. Section 1 is marked. Earlier we have seen the distance from section 1 to orifice plate and distance from orifice plate to section 2, that we have seen in the previous slide. So P1 is the pressure at section 1. V1 is the velocity at section 1. A1 is the area of cross section at section 1. Okay. P2, V2, A2 are the corresponding notations at section 2. So applying Bernoulli's equation, P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2. Okay. Okay, we simplify the equation. In the second step, we bring the terms of pressure head and potential head to the left side, and we bring the kinetic energy terms to the right side. The equation for H, which we have already seen in the derivation for Venturi meter, is P1 by rho g plus Z1 minus P2 by rho g plus Z2. Okay. And also, see, if the pipe is horizontal, then Z1 and Z2 can be cancelled. So only P1 by rho g and P2 by rho g are here. So H becomes equal to P1 minus P2 by rho g And again the right hand side, h is equal to V2 square by 2g minus V1 square by 2g. Okay, so V2 is equal to square root of 2gh plus V1 square. Okay, from this equation. So at section 2 is the vena contracta and A2 represents the area at the vena contracta. Okay, if A0 is the area of the orifice, then we have CC, which is the coefficient of contraction, that is A2 by A0. That is A2 is the area at section 2 or area at the vena contracta divided by A0, which is the area of the orifice. So ratio between area of vena contracta and area of orifice gives you the coefficient of contraction. Okay. So we can also write A2 is equal to A0 into CC. By continuity equation, we have A1 V1 is equal to A2 V2. Okay. So V1 is equal to A2 by A1 into V2. Okay. Or we can substitute for A2, that is A0 into CC by A1 into V2. So this value of V1 we can substitute in the equation for V2. So V2 becomes square root of 2gh plus A0 square into CC square into V2 square by A1 square. Okay. So this term we can simplify as, we can square both sides. So we get like this. Again finally bringing V2 to the left hand side and all the other terms to the right hand side, we get V2 is equal to square root of 2gh the whole divided by 1 minus A0 by A1 the whole square into CC square. Okay. Q is equal to V2 into A2, that is discharge is equal to V2 into A2. A2 is equal to A0 into CC, that we have substituted here. Okay. So Q is equal to A0 into CC into square root of 2gh the whole divided by 1 minus A0 by A1 the whole square into CC square. And it can be simplified as below, that is CD is equal to CC into square root of 1 minus A0 by A1 the whole square divided by square root of 1 minus A0 by A1 the whole square into CC square. Okay, that is the coefficient of contraction is represented in terms of the coefficient of discharge. Okay. Okay. Just before we came to an equation which gives coefficient of discharge CD in terms of coefficient of contraction. This we can also write in the form where coefficient of contraction is given in terms of coefficient of discharge. Okay. And substitute this value of CC in the equation for discharge Q. So it becomes A0 into CD into square root of 1 minus A0 by A1 the whole square into CC square by square root of 1 minus A0 by A1 the whole square into square root of 2gh the whole divided by square root of 1 minus A0 by A1 the whole square into CC square. So this whole term gets cancelled here, right, and the denominator here goes into the numerator. So finally it becomes CD into A0 into A1 into square root of 2gh the whole divided by square root of A1 square minus A0 square, and CD is the coefficient of discharge for the orifice meter. Now we can see some problems. An orifice meter with an orifice diameter 10 cm is inserted into a pipe of 20 cm diameter. The pressure gauges fitted upstream and downstream of the orifice meter gives readings of 19.62 Newton per centimeter square and 9.81 Newton per centimeter square respectively. Coefficient of discharge for the orifice meter is given as 0.6. Find the discharge of water through pipe. So here the diameter of the orifice is given. So we can find out the area of the orifice. The orifice is circular in cross section. And again the diameter of the pipe is given. So we can find out the area of the cross section of the pipe, which is again circular. Again P1 is given, which is the reading of pressure at the upstream, that is at section 1, as 19.62 Newton per centimeter square. We convert it into Newton per meter square by multiplying with 10 raised to 4. Okay. Then we need the term P1 by rho G. So P1 divided by rho. The fluid in the pipe is water, right, in the question. So rho is 1000 for water and G is 9.81. So it becomes 20 meters of water. P1 by rho G becomes 20 meters of water. So P2 by rho G is given by 10 meters. Okay. So H is finally given by P1 by rho G minus P2 by rho G, as we have seen during the derivation. So that is 20 minus 10, which is equal to 10 meters of water or 1000 centimeters of water. So coefficient of discharge is given as 0.6. Okay. So the equation for discharge is Q is equal to CD into A0 into A1 the whole divided by A1 square minus A0 square into square root of 2GH. Okay. So substituting all the values which we know, that is A0, A1, H, CD and G, we get the final answer as 68,213.28 centimeter cube per second, which is converted to liters per second. It comes to 68.21. Okay. Let's see the second problem, where orifice meter with orifice diameter 15 centimeter is inserted in a pipe of 30 centimeter diameter. The pressure difference measured by a mercury oil differential manometer on the two sides of the orifice meter gives a reading of 50 centimeter of mercury. Find the rate of flow of oil of specific gravity 0.9 when the coefficient of discharge of the orifice meter is equal to 0.64. The details given are the diameter of the orifice, which is D0. So we can find out the area of the orifice, that is A0, circular cross section. Again diameter of pipe is also given, so we can find out the area of the pipe which has circular cross section. Specific gravity of oil is given, which is 0.9. So S0 is equal to 0.9. Reading of differential manometer X is 50 centimeters. Okay. So the differential head, that is the difference in pressure between sections, is given by H, which is equal to X into Sg by S0 minus 1. So S0 is the specific gravity of the oil. Sg is the specific gravity of the liquid in the manometer, which is 13.6, that is mercury is the liquid, the manometer. S0 is equal to 0.9. 50 is the manometer reading, X. So H is equal to 705.5 centimeter of oil. CD is given as 0.64. So the rate of flow is given by the equation Q is equal to CD into A0 into A1 the whole divided by square root of A1 square minus A0 square into square root of 2GH. So we know the quantities A0, A1, H and G. CD is also known to us. So finally we get the answer in centimeter cube per second. We convert it to liters per second as 137.414 liters per second.